Hello everyone, thank you for joining me today. Today I would like to increase your knowledge of supercapacitors and how to do the proper part selection. My name is Jason Lee. I'm Global Product Manager at Eaton for our supercapacitor products. I've been working with supercapacitors, or some call them ultracapacitors or EDLCs, for the last 15 years. Today I will talk about different energy storage types, some of their general advantages and disadvantages. I'll give a brief applications overview, but the meat of the presentation will go through the calculations to properly select a supercapacitor product and how to make adjustments for lifetime considerations. Let's talk about different energy storage types. This will not be an exhaustive list or analysis, but a very high-level view to compare different types. Many of you have seen what's called a Ragone plot, which shows power and energy on the two axes. In this plot, the x-axis shows specific power in watts per kilogram, and the y-axis shows specific energy in watt-hours per kilogram. You could do a similar plot per cubic meter to normalize the technologies. The upper left are very energy-dense technologies, and as you move to the bottom right, to more power-dense. Of course, the goal for research and development is actually to move the technology to the upper right for both the power and energy dense technology. The other feature of this plot is that you can draw lines of discharge times, energy divided by power, to get an idea of the optimal charge and discharge times. These are shown by the diagonal lines plotted. If we look at traditional capacitors in the bottom right, like electrolytics, you can see that they have a lot of power but very little energy. This lends them very well to short, high-power discharges, typically less than half a second, and even much shorter. This is why they're used for many filtering applications. As you move up in energy, supercapacitors occupy an ideal timing of 1 second to under 1 minute discharge times. I will note that you can technically design systems for much longer times, but they become either too large or too expensive. The next technology that we'll talk about as we go to longer discharge times are hybrid supercapacitors. These are ideally used for discharge times between 1 and 5 minutes. They have some other features which I will talk about which can apply to shorter discharge times as well. As we keep moving to higher energy but lower power, I put all of the battery technologies in one bubble. They could be separated into each technology, but for this comparison, we'll treat them somewhat the same. We see different battery technologies being used from 3 minutes up to several hours. Then as you move further to the left and longer discharge times, you can get to other technologies such as fuel cells. I will not cover those in this presentation. How do they work? A supercapacitor is a very simple device. It is made up of two electrodes, typically of activated carbon, although we are starting to see some new materials such as graphene and carbon nanotubes getting closer to production. There's an electrolyte which allows ions to polarize as the device is charged. You can see the top picture. When fully charged, there are layers of ions on each surface with a solvent in between. This creates two capacitors in series internal to the device. From an electrical standpoint, there is a linear drop in voltage as the device is discharged under constant current. Since the device only moves charge around as it's charged and discharged, it has extremely high cycle life, almost limitless. Comparing to batteries, which have some of the similar materials, the storage is by electrochemical processes, meaning chemical reactions. One electrode is typically graphite and the other a metal oxide. This is in lithium-ion batteries. The power is limited due to the chemical reaction and much more temperature dependent. The electrical profile is much flatter with respect to discharge until near the end of the capacity when it starts to drop. A hybrid capacitor, or today a lithium capacitor, is an asymmetric device which is a mix of battery-like features on the anode and a traditional supercapacitor on the cathode. So the anode is typically graphite doped with lithium, and the cathode pure activated carbon. As new products are developed, we may see new materials on the anode. In terms of performance, the device falls between a supercapacitor and a battery. However, the linear operation region on the cathode side gives charge-discharge cycling, temperature, and lifetime characteristics closer to a symmetric supercapacitor. Thus, in normal operation, it has a linear drop in voltage under constant current. However, there is also a minimum operating voltage to stay in this linear region in order to keep a long lifetime. Over-discharging the device below its rated minimum voltage will cause an accelerated degradation as the lithium is leached out of the anode. Here's a high-level comparison of the features of the different technologies. Supercapacitors provide great power and lifetime, whether it's cycle life to the millions of charge-discharge cycles or up to 20-year calendar life. They also operate under the widest environmental conditions in terms of load cycles and temperature. Hybrid supercapacitors have higher energy density with similar lifetimes, but are much more limited in temperature range and power. They can be used effectively in tandem with batteries to provide long life and pull power away from the batteries. Their extremely low leakage current reduces battery drain. Both traditional supercapacitors and hybrids provide outstanding safety and environmental friendliness with no thermal runaway. Of course, the primary advantage of batteries is energy density. Let's look at a few popular applications. Supercapacitors play across a broad range of industries and in several different applications within these industries. I have omitted consumer applications on this chart. Coin cell formats play across all industries for real-time clock backup. Then you can see here there are both cylindrical, board-mounted cells and larger modules for various applications. In computing, the dominant application has been backup power for memory cache. More companies are starting to look at supercaps for backup power for data centers and telecom base stations as well. Transportation has seen engine starting, safety systems, and wireless communications for transmissions and tracking. In the energy markets, there have been three major applications: electric meters for data transmissions to reduce peak power in the meter and provide data when the power goes out, water and gas meters to improve the performance of lithium-thionyl batteries, and backup power for wind turbine pitch control. We're starting to see larger systems for grid support, microgrids, and renewable firming starting to wrap up over the next several years. Industrial markets is a catch-all for what doesn't fit into the other markets. We are seeing some applications stand out, with warehouse automation and industrial UPSs growing. Warehouse automation takes advantage of quick charge-discharge capability and cycle life, while industrial UPSs are growing due to short duration needed for ride-through power variation, which can cause hours of downtime in wide varying temperatures. Other applications include PLC controllers for safe shutdown and ride-through, industrial equipment for safe shutdown. But there are literally hundreds of applications in this space. Medical markets have been strong for peak power shaving and UPS application. If a facility does not have sufficient utility power, supercaps are used to provide peaks needed for MRI, CT, and PET scanners. These same supercapacitors are also used in diagnostic and safety equipment for power ride-through, power alarm systems in case of a power outage. This chart gives a high-level overview of different formats and types of supercapacitors. They go from lower capacitance and voltage to higher voltage and capacitance as you go left to right across the page, except for the hybrid cells on the far right, which are more of a cylindrical format cell. Other than coin cells, most applications use multiples of particular product. You can see, again, some of the applications that I talked about on the previous page and general power levels and discharge and charging times associated with the different product types. Coin cells typically run nanoamps or microamps for days or weeks for the RTC backup. Cylindrical cells will go to higher power up to tens of watts and up to a minute. Large cells can either be board mounted in the 300 to 600 farad range, or their larger end when we get into the several thousand farads per cell and connected with bus bars. These typically run up to 1 minute but there have been applications where they'll run up to 5 minutes on the grid. Modules use the higher end of the large cells to include mechanical and environmental protection, but also provide cell management to optimize lifetime and safety. These modules are typically designed for systems in the 10 kilowatt to multi-megawatt size. There are more and more put into cabinets with circuit protection to provide a full energy storage subsystem. All supercap applications fall into one of three use models. Peak power, where the main power source, whether it's utility power, a battery, fuel cell, etc., cannot provide the peak power needed. We see this often in devices with radio communications, where the rest of the device is very low power, except for the LTE or 5G radio. The supercapacitor provides power when data transmissions are needed. The second use model is for backup power. When the main power is lost or partially drops, the supercaps can fill in that short-term power loss. These can be full UPSs, as discussed on the previous slide, or embedded backup power into an existing device. The last use model utilizes the storage capacity for both charging and discharging. The classic cases are hybrid vehicles in which supercapacitors are most efficient at capturing braking energy and then reusing it for acceleration. Many grid and microgrid applications use the same model to balance electric supply and demand. On a slower scale, IoT systems can follow this as they accept charge from different types of generators like small solar panels or other energy capture devices, and then use that energy for communications. Looking at a little more detail of popular applications, we can think of the industrial Internet of Things to include smart meters as the early networks, but more recently we see them in chemical factories and agricultural systems. They capture energy from solar, piezoelectric, and thermal devices. The energy is then reused for communications or maybe actuators and valves. The key features to use the supercapacitors are the long lifetime, wide temperature range, and environmental range. In cases where a battery is also needed, they can provide peak power with very low battery drain, particularly in the case of using them with hybrid supercapacitors. Engine starting has been a popular use for supercapacitors for a long time, from microhybrid stop-start in cars to heavy trucks, construction equipment, generators, and boats. The high peak power, longevity, and ability to relieve batteries of the high starting currents, which ultimately cause the batteries to fail. Industrial UPSs commonly use supercapacitors due to requirements for high and low temperatures in the operating areas of factories and chemical plants. The long, predictable life of supercapacitors allows them to be used for the life of the UPS with no changes. Many locations where plants operate may not have full outages, but have many small variations that can cause controllers to fail and take the plant down for hours. Bottling plants, chemical factories, injection molding plants, and semiconductor manufacturing are all using supercapacitors for power quality improvement. One of the newer applications in the last 5 years is in material handling. As online shopping increases, automated warehouses have seen huge growth. Supercapacitors are powering robots to move material on pallets in traditional automated guided vehicles, or AGVs, and in ASARs, or automated storage and retrieval systems. The ability to quick charge, withstand high shock and vibration, and charge and discharge millions of times makes supercapacitors the best energy storage technology here. Other applications in material handling are at seaports, where supercapacitor high peak power allows ports to increase capacity without new utility infrastructure, which saves huge capital costs. The last application I'll talk about is grid storage. This can be true grid energy storage connected to the distribution system or on microgrids. Firming of renewable output was the first use of supercapacitors in this space. The high power, fast charge and discharge of supercapacitors matches well with the variation of solar output as one example. More recently, as we have seen different generating resources entering the grid that have less inertia than traditional turbine generators, there is a need to inject power using STATCOMs and avoid voltage and frequency variations on the grid. Supercapacitors are also being used in solar systems with batteries. This is to optimize the solar output and protect the batteries, which are primarily being used to time shift the energy. So how do we find the right supercapacitor design for a particular energy storage system? First, some basic equations. These are the same equations for all capacitors and what we all learned in physics or some engineering class. The values used change depending on what type of capacitor, but not the equations. So we have the current in a capacitor is the capacitance times the change in voltage with time. And energy is 1/2 of the capacitance times the starting voltage minus the ending voltage of the charge or discharge. In circuit analysis, you also have that the voltage across the capacitor is the current times the discharge time divided by the current from the first equation, plus the voltage drop due to internal resistance, or ESR. This last term takes into account the reality of a non-ideal capacitor, which would typically have 0 ESR. Some additional questions for capacitors in series are that the capacitance divides by the number in series and the ESR multiplies. Conversely, capacitance in parallel, the capacitance adds and the ESR divides. If we look at a discharge curve shown in the upper right, under constant current, you get an initial voltage drop due to ESR, then a linear drop in voltage due to capacitance, where the capacitance is the current divided by the slope of the line. About designing a system, we need to know some system parameters. Then we can make adjustments for other factors such as lifetime, duty cycle, and temperature. We first need to know the maximum and minimum operating voltage of the system. Then the capacitors will be selected to fit the discharge curve within these limits, since the voltage drops as the device discharges. Obviously, we need to know the power or current needed and the time. You might also have a maximum voltage to meet the above operating voltage. This might be due to the possibility of an overvoltage condition. I've seen this most often in automotive applications where they must account for a load dump occurrence. Let's take an example. We have a 16-volt system which can operate down to 9 volts. The load requires a constant 4 amps for 5 seconds. We can get an estimate of the capacitance needed by ignoring the ESR drop, using equation 3 from the previous slide, with 4 amps for load current multiplied by 5 seconds, and the total voltage window of 7 volts, we find that we need 2.86 farads. This is the capacitance for the system, not necessarily a single capacitor. To get to the number of cells needed, we start with the number in series. The voltage multiplies by the number of cells. So the most common cell today is a 3-volt cell. This requires 6 cells to get to 16 volts. We can then use equation 4 to determine the cell capacitance. In our example, 2.86 farads times 6 cells equals 17 farads. It is possible that the capacitance will come up much higher than any cell available, and you may need to add cells in parallel to get there. We assumed a 3-volt cell on the previous page in our voltage calculation. So looking at the possible selections, we need one with at least 17 farads, so we pick a 25 farad cell. Now we need to check for the total voltage drop at the end of the discharge by adding back in the ESR term in equation 3. The values for the capacitance of the system are 25 farads, the cell value, divided by 6, and the ESR of 18 milliohms times 6. This will give a total voltage drop of 5.23 volts. Since this is less than the voltage window from the application, which is 7 volts, the design should work. Now let's look at a case. What if your load is not constant current, as most loads are not? the voltage drop due to ESR becomes more challenging. We take a similar case to the previous example, but instead of a 4 amp load, it is 60 watts. There are two methods of approximation: a current approximation and an incremental calculation. We'll first try method 1. You can make an approximation to calculate the average current. This is not exact since we do not know the actual minimum voltage at the end of discharge to properly calculate the maximum current. But we can use this approximation, take the average current, and plug it into the constant current case. Here we still get a 25 farad cell, but the capacitance is actually needed is 22 farads instead of 17. But the system works with a 25 farad cell. The second method to calculate for a constant power case is based on the energy needed from equation 2. We need to assume that the full voltage range allowed by the system is used. This may not be the case, but that's where we start. 60 watts for 5 seconds is 300 joules, so this is the total energy needed for a discharge. Plugging this into equation 2 and solving for capacitance with a 16 volt working voltage and a 9 volt minimum voltage, we get 3.43 farads. Due to the 16 volt operating voltage, we still need 6 cells, so the cell capacity is just over 20 farads, and again, a 25 farad cell works. The previous two methods were an example to show the calculations, but neither really calculates things properly. With method 1, we underestimated the voltage drop due to ESR since we used the average current. This underestimates the total voltage drop and therefore underestimates how much capacitance will be needed. With method 2, we did not take into account the voltage drop due to ESR at all, so again, the capacitance is undersized. The best method is to use a stepwise calculation to simulate the discharge curve, calculating the current and voltage drop due to both energy used and ESR drop at each step. This combines methods 1 and 2, but the equations are not necessarily straightforward. In using equation 3 to calculate the voltage drop in the spreadsheet, we divided the discharge into 40 time increments. This way, as the current increases, we increase the voltage drop due to ESR. The smaller the time increment, the more accurate the calculation will be, but in this case, we've shown 40 step increments, which seems to produce good results. So we have the time in the first column, the supercap voltage under no load in the next column. The supercap current is calculated in the third column. The fourth column is the power, and then the next column is the terminal voltage at the end of each discharge under load. And this is the critical voltage to compare at the end of the full discharge to compare to the system requirement, in this case 9 volts. With this, we can generate the voltage and current curves versus time to make sure the voltage does not drop below the minimum operating voltage required. One other feature is you can see the initial voltage drop due to ESR with the voltage curve starting below 16 volts. To come up with the optimal size, you can input different cell parameters and configurations into the tool to get the best design, typically the fewest cells. So we've covered the basics of calculations with the system and application requirements for voltage, power or current, and product selection. We can look at effects which will change the design some. Things like temperature, lifetime expectations, maximizing lifetime, and duty cycle and self-heating effects. First, look at temperature and life effects on our calculations. These are the two most common factors to make adjustments in the calculations. Supercapacitors drop in capacitance and increase in ESR over time. Depending upon the product type, the capacitance drop at the end of life is typically defined at 20% or 30% of the initial value, and ESR increases 100% to 300% of the specification. In this example, for a 3 volt cylindrical cell, I use a 30% capacitance drop and 100% ESR increase, or 200% of the spec for the ESR value. If your device needs to work over temperature range, we need to take that into account. temperature affects the ESR and to a lesser extent the capacitance. A typical temperature effect at minus 40 degrees C is a 10% decrease in capacitance and 60% increase in ESR compared to the 25-degree value. Combining these two factors yields a 37% drop in capacitance, or 63% of initial value, and 3.2 times the datasheet value of ESR. These factors are multiplied into the equation in our constant current example for both the capacitance and the ESR. It yields a voltage drop of 8.63 volts, which is greater than the 7-volt window allowed by the system requirements. To solve this problem, we go back to the product selection and pick a 35 farad cell. This gives us specifications of 35 farads and 15 milliohms, which we can then calculate for a 6.59 volt drop. This is within the 7-volt system specification. So we again have a working design. Some other factors which can affect your design are primarily temperature related. Self-heating from frequent high current charging and discharging can drive the temperature of the cell up. Normally we're only concerned about longer term effects which can affect the lifetime, so we use the RMS current. Each supercapacitor has a thermal resistance, RTH, which gives a temperature rise based on the current and the ESR. You can reduce the temperature rise by selecting a cell with a lower ESR, normally a higher capacitance cell, or adding active cooling to reduce the thermal resistance. If you have a single high power discharge and want to know the temperature effects, you'll need the heat capacity, CTH. Since this does not typically have long-term effects on the lifetime, it is not normally published, so you may need to contact the manufacturer. Generally, whether due to self-heating effects, high ambient temperature, or just the need for a longer life of your design, adding cells in series will offset, giving longer life and offset temperature issues. So in our example, going to 7 cells would yield a longer product life before reaching the 30% capacitance drop or 100% ESR increase. Please note that when you add a cell in series, you may also need more capacitance, since the capacitance will drop with more cells in series as the capacitance divides by the number in series. Another approach is to add active cooling. Most commonly this is forced air, but in rare cases we have seen water cooling systems or perhaps thermoelectric coolers. There's a lot of interest in cell management or cell balancing. In contrast to battery cell balancing or BMSs, which maintain safety, the primary purpose of cell balancing for supercapacitors is to keep the voltage the same so that system lifetime is maximized. There are 3 basic designs, but also multiple IC designs that use different techniques. As far as discrete designs, there are 3 that the industry has used: passive, what I'll call an active shunt, and truly active. In most cases, the supercapacitor manufacturers have used the first 2. Passive is the most simple and merely puts resistors in parallel with each cell. This does a great job of balancing, is the lowest cost solution, but is also the least efficient. Since it's always running, it's always discharging. It's typically used for backup power applications where you have a constant power source. An active shunt uses a FET to turn on at a fixed voltage, but then it is a resistive discharge. The voltage turn on is typically near the rated voltage, so balancing is somewhat limited if the operating voltage is below the rated voltage, as is typical to meet lifetime requirements. The system protects against overvoltage, but does less balancing. It's the most efficient since it is not balancing most of the time. Truly active design moves charge between cells to keep the voltage balanced. While this would seem to be the best method, the efficiency in moving charge may override the savings. It becomes complicated with high cell count designs, and further if multiple modules are used, as communication is needed across all the cells in order to do the balancing. To wrap up, we looked at how to make calculations to come up with a supercapacitor design, but instead of doing manual calculations, you can go to the Eaton website to find a web-based version of the spreadsheet I showed earlier. Go to eaton.com/supercapacitors, scroll to the bottom to find the supercapacitor calculator. Input your design requirements in step 1, simply the parameters that I showed earlier in the calculation for system voltage, maximum and minimum, operating voltage, power or current, and time of discharge. You can select a product in step 2. There are some filters there for coin cells, cylindrical cells, modules, and some application requirements. It'll give the results to go along with the graph, shown here on the right. You can add cells in series or parallel strings to see the effects and change the derating factors for end of life and temperature effect. By default, the derating factors use end of life conditions, but do not assume anything for temperature effects. If you have a more complicated load profile or need lifetime estimates, you can reach out to Eaton for help. There's contact information at the end of the presentation. To summarize, we've shown that supercapacitors have become commonplace for many applications. Newer hybrid supercapacitors have extended the application space and discharge time. A key in applying the right energy storage technology is to evaluate typical discharge times for supercapacitors, hybrid versions, and batteries. These apply with the exception of real-time clock backup, in which supercapacitors are used for days or weeks. Electrical design of supercapacitors uses basic electrical engineering and can take into account environmental effects. Online tools and applications engineers are available to help you with your designs, which can be from microwatts to megawatts. So let's get designing. And thanks for your time.